Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, let's do the Python part of module number 11, Principal Component Analysis. So in the theory lecture, we talked about PCA, Kernel PCA, and we did some visualizations. We worked with USA arrest dataset. And now in this video, the goal is to replicate all those things using, in Python, okay? So let's go ahead and open the folder, machine learning, go to the lectures and codes, module 11, Python. You're going to see 3 notebooks and 3 datasets, right? So the notebooks are named as PCA PCA, PCA Sklearn, and Kernel PCA. So I'm going to work with 2 packages. One of them is obviously our familiar Sklearn, which is heavily used in machine learning community. And the other one that I found interesting for this PCA module is the package called PCA, right? Literally the small letters PCA, okay? And I'm going to show you how to work with both of them, how to just get the same answers using either the PCA package or the Sklearn package, right? I like the PCA package because of some of these simple visualizations that it have. But honestly, today with the help of ChatGPT or I don't know, any other large language models or GitHub Copilot, you can replicate these graphs very easily. So I'm not quite sure if there's enough reason for us to just work with yet another package in Python, but because this is too simple to work with, I'm going to go ahead and show it to you how to do that anyways. It's going to be a quick one. And then we're going to go look into another notebook. This is using Sklearn package. PCA, and once we want to do Kernel PCA, it's only available in Sklearn. So let's go ahead and look into those ones. Starting with the simple one, PCA PCA. So it's using the PCA package. So if you click on it, you should be able to open it in Google Colab. And if you want to run it on Colab, make sure you make a copy to your own drive, connect it to the server, and then let it run. And just make sure that, again, if you're doing it in Google Colab, because PCA is not installed already, you have to go ahead and do pip install PCA. Okay, I'm gonna run these things on my local computer. So this is actually, let me go back to the file. So these are the 3 notebooks: PCA PCA using PCA package, and then PCA Sklearn and Kernel PCA using Sklearn package, right? So starting with the first one. So I'm already in an environment that I have PCA installed, so I don't need to install it. But again, for you guys, if you don't have it, if this is the first time, you have to go ahead and do pip install. So let's go ahead and import the relevant libraries and then set the random state. And from PCA package, let's import PCA. Okay. Again, if you don't have it, just do pip install local computer. If it is on Google Colab, do exclamation pip install. All right, so this is a USA arrest dataset. It's on my GitHub account, and you can find it there. And this is a dataset that we already looked into in the theory lecture. There are 50 states. We have 4 features: murder, assault, urban population, and rape. And then we want to do some 2D visualizations and then basically locate these states based on those features, right? But we know that we cannot visualize it in 4 dimensions, so that's why we are using principal component analysis to visualize it in 2 dimensions, right? So basically replicating this. Let me zoom in a little bit. If you want to replicate this pie plot and then replicate this table, this is basically our loadings for principal component 1 and principal component 2. So let's go ahead and see how easily we can do it with PCA package. Again, for PCA, in general, for all the machine learning models, I think theory is more important to understand, because when it comes to applying these things in Python, again, especially today with ChatGPT, it's super simple. It's really easy. But anyways, okay, so let's go ahead and create this X feature. These are the features. I call it X. Obviously, we need to go ahead and drop the state variable. However, I'm going to save it as a state for just visual purposes, right? Later on, we're going to use this state. So let's go ahead and run this. Again, our data is this, 4-dimensional space with these features. Okay. So once you have imported that module, PCA library, then you can create an object, call it model. You can call it anything. You can call it PCA model, but I just wanted to avoid using too many PCAs. So I call it model, and then this is PCA. You can say number of components is equal to whatever. So at most we can have 4 because we have 4 features. You cannot have more principal components than number of features if your model is linear PCA, right? For kernel PCA, if you have watched the theory lecture, we know that we can have as the number of observations PCAs, right? So I'm going to get into that when we get to the kernel PCA. But for linear PCA, obviously here we can have a number of components equal to 4 or less than that. Okay, so I'm going to go ahead and start with 4. And then a cool feature about the PCA package is that you don't need to scale the features manually. If you do normalize equal to true, it's going to do a simple standardization for you. So if I run this, that's pretty straightforward. Now the model has been created. I just need to do fit transform, right? Because I'm going to say this model.fit transform and apply to my X features, right? So basically I'm applying this transformation. Guys, when I run this, all the eigenvalues, eigenvectors are calculated, blah, blah, blah. We know the loadings and everything, right? So when I go ahead and do the fit transform, right? So now we are going from this, let's say, space to this space, which is principal component space. So this is results, and in this result, it's a dictionary, and we're going to see, we can go ahead and extract some of the interesting components of the model, right? So if you run it for the first time, you're going to see these things, you know, extracting columns labels from data frame, extracting row labels from data frame. Because I have run it previously, if you run it again, it says that cleaning previous fitted model, right? And yeah, it's going to normalize the inputs for you. It's going to reduce the dimensionality. Here, it's not going to reduce the dimension because we're going from 4 dimension to 4 dimension. But anyways, if I change it to 2, it's reducing dimension as well. And we're looking into loadings. And what are the loadings? Loadings are these files, right? This is, actually, let me see if there's a slide for that. I think, yeah, these are our loadings, right? Principal component 1, if I have 4 features, it's going to have 4 loadings, 5, 1, 1, 2, 1, 3, 1, and 4, 1, and etc. Okay, so these are the loadings, and then it can go ahead and compute explain variance. And we know that principal component analysis is used for anomaly detection as well, or outlier detection. But basically, that's beyond the topic of this course. But we know that in practice, we can use PCA with the hoteling the test to just find the outliers, right? Yeah, okay, so again, this is our results. Inside this result, this is what we see. Loadings for 4 features, right? For 4 components. Then we have scores. Remember, principal component 1, these are the scores, right? We have 50 states, we're going to have 50 scores, okay? So basically, in this example, we go from 50 by 4 dimension, 50 observations, 4 features, to 50 observations, 4 principal components, right? So we're not reducing the dimension. What else do we have? We have something called explain variance. And so what is it? So basically this is our cumulative PVE. So let me pull up the slide quickly. And this one, okay? So we talked about proportion variance explained, the proportion of the variance in the data, which is explained by principal component number 1, component number 2, and etc. We call it PVE. And the cumulative version is just cumulative PVE, right? So this explained variance is the cumulative PVE. So the first component is explained 62%, the first 2 components 86%, the first 3 components 95%, and the first 4 components, which happens to be all the components available, it's going to obviously explain 100%, right? Variance ratio is what we used to call PVE, right? So first component 62%, second 24%, third 8.9%, and fourth 4.3%. Yeah, that's pretty much everything you needed to know from that results dictionary, right? Then you can go ahead and obviously save them separately. So for example, loadings, I'm going to save it as a separate object, and I'm going to transpose it to just make sure that this is similar to what we had on the slides. However, on the slide we had 2 components. Here I'm showing you all the 4 components. So you can go ahead and pause the video, go back, and then just fit transform with 2 components instead of 4 components. We can save the scores. Remember guys, this was a dictionary. If I look at the PC components, and it's going to be all the scores. And the dimension of the scores is going to be the 50 by 4 because we have 50 states. All right. Now that we have an object which has been trained, well, I think trained is not the right word, but anyways, the data has been transformed. We can do model.plot, and if I do something as simple as this, model.plot, again, this is just for the fixed size, you can just ignore it. If I do model.plot, that's it, this is our scree plot. So basically component 1, component 2, 3, 4, this is a cumulative version, and this is the cutoff, right? So because I use all the components, so it's just telling me that the first 4 components explained 100% of the variance, right? Then we can go ahead and replicate our biplot, right? So this was our biplot that we had. Now if we just need to do model.biplot, and that's it, that's simple. And these are the 50 states in the transposed or transformed space, PC1, PC2. And these are the loadings, right? So these are the loading vectors. Okay. If I can do the same thing in 3D plot, so if I do biplot 3D, so it's going to give me the 3D version of that. Again, this visualization of the PCA package is really interesting. Then, yeah, we can look into the loadings as well. If you're curious, what are these numbers, for example, written here? Remember, we had 4 principal components, right? And it's only showing, and we had for the loadings, each loading vector has 4 elements, but it's showing only one of them. This package, it's showing the largest one, the most important one. So for example, remember for murder, just remember this number, 0.649. Let's look into the loadings. So the loading vector for murder is this, and the largest number is 0.649. Okay. Yeah. Then what else? So we have, so I think that's pretty much it. Now let's go ahead and use another data set and basically apply this same model to that, right? So here's another data set. It's called market data, and it's a data set of the basically, here's the head of data. The data itself has 4,451 observations with 99 columns, which 2 of them are irrelevant, stock ID and date are irrelevant, so we have 97 features, right? And these are mostly financial ratio features, right? So for example, I don't know, we have asset turnover, we have capital expenditure, we have total capital, total debt, you name it, right? So we have 97 of these features, right? And so this is pretty much close to the example that we cover from the CFA textbook in the theory lecture, okay? So yeah, let's see if there's any NA in the data set. So again, these are all the financial ratios. And the goal is to just reduce the dimension, because right now we have 97 features, and we want to see, can we reduce it to a level that still it can explain 80% of the variation in the data, right? So that's the goal. We make sure that there's no NA in the data set. Again, we're going to go ahead and drop the stock ID and date from the data set. And then, yeah. So here's another way of using this PCA package, right? PCA module. If I do number of components equal to any integer number, like 2, 3, 4, it's going to be the number of components, right? However, I have the option to pick a number between 0 and 1, not including 1. This means that, so you have to interpret it like this. Go ahead and create principal components until it explains 80% of the variation in the data. So this is really cool. If I change it to 90, it's going to go ahead and increase those components. If I change it to 60%, it's going to go ahead and decrease those numbers, right? So let's keep it to 80% and then normalize equal to true. So here is our model. Let's apply it to the data. Oh, let's see. I think probably I didn't run this one. Yeah, let's see. Because if there's an NA in the data set, yeah, it's going to complain. Okay, so yeah, we can look into the results, but we have seen this before. So I can just pull up the loadings, and these are going to be, we ended up with 14 components, by the way. So remember, I didn't specifically tell the model that use 14 features. I say use as many features, create as many principal components as you need to explain 80% of the variation of the data. And the answer was 14, okay? So these are the loadings. We can look into the scores. Okay, so these are the scores, and obviously we can look at the scree plot. If I do model.plot, this is my scree plot. And here, again, we needed 14 principal components to explain greater than 80%. Here it happens to be 82.56% of the variance, right? So this is a cool feature of the PCA package. Okay, yeah, that was pretty much it. So now next, let's use Sklearn and PCA, the linear PCA with the Sklearn package. Okay, so this is the second notebook that we're going to work on. All right, so the second notebook, PCA using Sklearn package. So let's go ahead and import the relevant libraries and then setting the random state to 1000. Let's work with another dataset. This dataset is called Wine dataset. It's actually one of the more famous one when it comes to clustering techniques and PCA, in the machine learning community. So if you're curious about the dataset, you can check out this documentation, basically telling you what is this data set, what is the task, and etc., right? So we have a bunch of variables here, the level of alcohol, malic acid, ash, and etc., Again, I'm not an expert, but the idea is that we have a bunch of features and we have also some clusters in the data already. So let me actually show you the head of data set, and it should make more sense, right? So here's the head of the data set, and again, we already have some customer segments. So this dataset is labeled already. So we are going to apply PCA to a labeled data. Obviously, we're not going to use labels, right? But I want to show you that. So for example, here we have, let's see, we have 13 features, and you want to see if I use, I don't know, 5 features. If I create 5 principal components, can I explain 80% of the variation in the data or not, right? Something like that. And then we can use it to basically as part of the supervised learning model and see if the performance of the model is going to get any better or worse, right? Again, for some models, we talked about all these things in the theory lecture. In some models, when you reduce the dimension, the performance is going to become better. Maybe some KNN model, which is suffering from curse of dimensionality. But in some other models, no. It all depends on how many components are you using, and those components are explaining what percentage of the variation in the data as well, right? If you're using 3 components, which is explaining only 20% of the variation of the data, obviously this model, this new supervised model using these principal components is going to underperform the original model. But you get the idea. We can still explore creating these new features, let's say engineering these new engineered features like principal components in our supervised environment, and see if we can get any better with that meta model, if you wish. Okay, so yeah, let's look into the info of the data set. There's no missing variables, and these are some characteristics of the wine. And then we have customer segments, right? So obviously if I go ahead and show you in this data set, what is the distribution of the customer segments, we already know that there are 59 customers in segment 1, 71 in segment 2, 48 in segment 3. I think it's a good idea to see, for example, if the segments are different in terms of averages, right? So I'm going to go ahead and use some group by. I say, hey, this data set, group by it by customer segments and report the averages, right? So this means that basically these are your segments. And for example, for the first variable, this is alcohol level. So segment 1 is 13.73, segment 2, 12.28, segment 3, 13.15. So it seems that there's a difference between these customer segments when it comes to alcohol level, I don't know, ash, magnesium, total, phenol, you name it, right? So the averages might be different, right? Or they might not. But anyways, this is a labeled data set. So we already know that these are customer segments, right? However, for our principal component task, obviously we're not going to use the labels. So I'm going to go ahead and drop this thing and apply the principal components to these 13 features, right? Hopefully that makes sense. Okay, so let's go ahead and do that. First things first, we know that we need to scale the features as well, right? So in the PCA package, we just need to use normalize equal to true. In Sklearn, we have to do it manually. So I'm going to go ahead and import standard scalar from Sklearn preprocessing and then create a scalar object. And then I'm going to go ahead and drop the customer segment because this was a labeled. We don't want to use it in the feature space. And then apply the scalar to that X. So that's it. So this is going to do the job for us. I have 178 observations with 13 features. Now let's go ahead and use principal component analysis. So from Sklearn decomposition, let's go ahead and import all cap letters PCA, and let's train a model, right? So I'm going to go ahead and start with 13 components, right? So I call this model object PCA. I think I would have been better off call it model, you know, for just make sure it's less confusing. But anyways, I'm going to call it small letter PCA. So this is the model object that we are creating. And let me actually show you the documentation really quick. The documentation for Sklearn, if you go to Sklearn decomposition, well, actually just Google Sklearn PCA documentation. The first link probably is there. So what are the options? We have number of components, and let me do a quick back and forth. What do I need? Yeah, that's pretty much everything we need, a number of components, right? And this can be a number, or just in the PCA package, it can be a number between 0 and 1, right? So let me show you. What are we doing? So right now I'm going to use 13 because I want to talk about how to calculate variance explained with different methods in Sklearn. So that's why I'm going to start with 13, right? So then off of this object, you can call a bunch of stuff, right? So for example, you can do PCA dots and see what is available. Components, explain variance ratio. You can get the covariance matrix. And why do we care? Because if I have the covariance matrix, I can go ahead and calculate the eigenvalues and eigenvectors. These are pretty much, you know, principal components and the loadings. That's it, right? So yeah, lots of cool stuff there. And here we can, for example, look into the number of features, 13, number of components, 13, and I can show you something very quick. I say, hey, go ahead and create principal components until you explain 80% of the variation. If I run this, obviously the number of features are going to be 13, but the components, well, 5. You only needed 5 components to explain 80% of the variation. Again, I'm going to go back and return it to 13 because I need to talk about something down the road. Okay, so the loadings, if I do PCA dot components, so these are going to be the loadings, right? And the shape is going to be 13 by 13 because we have 13 features and 13 principal components. That's why the loading shape is 13 by 13. If I go back and change it to 80%, we're going to get 5 by 13. We can transpose it and then see in a way that we saw on the slides, right? Okay, so let me go ahead and turn back to 13. Okay. So, by the way, I extensively use GitHub Copilot, and it's really convenient for coding. So I encourage you, if you haven't tried it, give it a try. Okay, so we can look at the first 2 principal components, right? So this is obviously it's going to have 13 dimensions. These are the loadings for. So PC1 is equal to 511 multiple. So this is your 511 multiply x1. 521 multiply x2, 531 multiply x3, and etc. Okay, so these are, if I do that calculation, I'm going to get the scores, right? So the scores, in order to get the scores, you can do PCA.fit transform. So automatically, if I do fit transform, it's going to save everything. Those are going to be the scores, right? So this is my scores. And now here's the interesting part. So we get to a point that we need to create proportion variance explained, right? The PVE. And then with that, we can create discrete plot. There are 3 different ways to calculate the PVE. So one of them is built in Sklearn, which we can use for the linear PCA. For kernel PCA, we cannot use that method. And the other ones is basically, if you have watched the theory lecture, it should be very intuitive. So it's nothing new. We have talked about all these things in theory, but let's do it in Python. Okay. So again, the first method is the built-in method. The second one is finding the contribution of each eigenvalue to the sum of all the eigenvalues. So imagine I have, 13 features, 13 principal components, and 13 eigenvalues, right? The eigenvalues goes from the largest to the smallest. If I look at the weight of each eigenvalue to the total sum of eigenvalues, this is going to be equal to proportion of variance explained, right? this second method only works if the number of components is equal to number of features, right? Because again, if you have, in this example, that's why I needed to use 13. In this example, if you have 13 features and if you reduce the dimension to 3, you're gonna get 3 eigenvalues, right? And that obviously is not gonna give you the PVE, proportion variance explained by all the components, right? The third method is finding the PVEs by looking at the proportional variance in the scores, right? So this is really interesting. I'm going to break it down why this method works. And the cool thing about this method is that it works for Kernel PCA as well. And actually, this is the only method that works for Kernel PCA. Okay, so, well, this one also, the number 2 will also work for Kernel PCA only if the number of components is equal to number of features, right? But with Kernel PCA, we know that number of components is equal to number of observations, so it's not gonna be the case. Okay, so let's work with the built-in method. So for the built-in method, it's super simple. If you just do PCA dot explain variance ratio, so it's gonna give you 13 numbers. Remember, I have 13 principal components, so these are going to be 13 numbers, right? So from the largest to the smallest. Component number 1 explaining 36%, component number 2 explaining 19%, and etc., etc. If I do the cumulative sum of this thing, it's going to give me the cumulative sum version of that, right? And yeah, the next one, if I do explained variance, this is going to give you the amount of variance explained by each PC, right? So this is the amount of variance explained by each PC. If you have watched the theory lecture, I want you to pause the video and think about it. What is this? The magnitude of the variance explained. What is it? This is your eigenvalues, right? So we're going to go ahead and create the eigenvalues, and you will see that the eigenvalues are exactly the same as this, right? So these are the eigenvalues. These are the proportional variance explained. So that was the first method, right? The second method is by simply go ahead and calculate the eigenvalues, eigenvectors, and look at the contribution of each eigenvalue to the sum of all the eigenvalues, right? Let's go ahead and do that. In order to do that, we need to get access to the covariance matrix, right? So remember, our X has 13 features. So what does it mean? It means that the covariance is a 13 by 13 matrix. So if I do PCA.covariance, this is going to give me the covariance thing, right? I'm going to save it as cov, and the shape is going to be 13 by 13, right? And by the way, this is a built-in method which comes with the PCA. However, for Kernel PCA, there's no get covariance. You have to do it manually. From NumPy package, you can do .cov, and then whatever X you have, you have to transpose it, right? So again, this probably we don't need to do xtrain. We will do x.t and then just covariance matrix. We have the covariance matrix here. Now we need to calculate eigenvalues, eigenvectors. So from NumPy linear algebra module, I'm going to import basically these two functions, eigenvalues. Well, sorry, the linear algebra, the eigen, DEIG eigen, the function, and then I just need to pass the covariance matrix, right? Because we talked about it in the theory lecture, at the core of principal component analysis is calculating the eigenvalues and eigenvectors of the covariance matrix. That's it, right? So I already have the covariance matrix of the original feature space. If I apply this function to that, it's going to give me the eigenvalues and eigenvectors as two separate objects, right? So let's go ahead and run it. Now we have access to the eigenvalues. These are going to be 13 numbers. Does this look familiar? If I scroll back up, there you go. So this is basically the amount of variance explained by each PC. If you go ahead and read the documentation of the PCA Sklearn package, you will see that, let's scroll down in the attributes. Yeah, explain variance, what is the other one? Let me actually try to find it. What is it? Yeah, explain variance. Yeah, explain variance is, yeah, there you go. The amount of variance explained by each of the selected components. So this is that magnitude that we were talking about. And we just calculated the eigenvalues. They're the same. So this is the same as eigenvalues. I have 13 eigenvalues. If I go ahead and take this one divided by the sum of all, it's going to give me the proportion variance explained. Let's give it a try. Here you go. So 36%, 19%, scrolling back up, 36%, 19%, and etc., etc. So this is working. So again, first method built in, second method look at the contribution of each eigenvalue to the sum, and then finally let's derive this proportion variance explained directly from the scores, from that transformed data, right? So this is the third one. So we have to go ahead and extract the scores first. And remember, the dimension of the score, because we have 13 components, it's going to be number of observations by 13 components, principal components, right? So why have scores? If I go ahead and calculate the variance of scores along the columns, it's going to be the contribution of each principal components in the total variance in the data. That's it, right? And I want you to pause the video, use ChatGPT, or think about it, that why we can simply apply the variance function to this score matrix along the columns PC1, PC2, PC3, and etc. And then that's going to give us, let's see, these ones, the magnitude of the variance. Why that's the case? Hint, principal components are orthogonal. Okay, so we cannot do the same thing to the X, which is the original feature space. It's not going to work. Well, it will work, but the numbers are going to be different. It's not going to be the same as the magnitude of basically eigenvalues, right? So yeah, the answer is that because these principal components are orthogonal to each other, the covariance is going to be equal to 0. So whatever is left is going to be the variance. Okay, cool. Now I have the magnitude of the variance. If I go ahead and divide each of these components by the total variance, and then that's it. This is the total contribution of each principal components to the sum, right? So 36%, 19%, and so as you can see, there are 3 different ways to get the same number, right? So obviously, if you're working with the linear PCA, just go ahead and use the built-in method. But if you're doing kernel PCA, you have to use the last method. Okay. So what else? Let's look into the scree-plot. So scree-plot, I'm going to go ahead and create a data frame by creating this dictionary, right? So the principal components are going to be between 1 and 13 in my example. And then I have 2 columns, PVE and cumulative PVE. The PVE is, we just talked about it. Let's use the built-in method, explain variance ratio. The cumulative version is just the cum sum version of that, right? So if I run this, I have a nice table and I can visualize it, right? So again, don't worry about these things. Honestly, don't worry about these things. You can use ChatGPT and then it can help you to create these ones. And after you have the code, go back and try to learn a thing or two from the way that people are coding out there. Because after all, GitHub Copilot or ChatGPT or any other LLM has been trained on the GitHub repository as well. So this is the way that people are coding, so it's going to help you learn from them as well. All right, so this is a scree-plot, and this is what we just created. And for example, here I'm going to show you the 85% line. So, and how many features, how many principal components do I need to get to that level of variation explained? So 6 of them. Is it 6? Yeah, I think 6, right? Okay. So that's the scree-plot. Again, using the PCA package, it was a lot easier. With Sklearn, it's a little more involved, but again, today you can use the internet as well. Okay, so then we can do biplot as well. So this was the biplot again. Yeah, this was the scree-plot. Sorry, this is the scree-plot. This is the biplot. So for biplot, we know that you cannot work with 13 principal components. You have to do two principal components, because after all, this is a 2D visualization. So we have to go ahead and retrain the thing. Now use 2 components, right? So let's use 2 components. And then obviously, this is the shape. I think it's a good idea to get a sense of the shape of the loadings, the scores, and etc., etc. And yeah, we can do. Actually, yeah. Here's the biplot for our data set, right? So principal component 1 is explaining 36%, component 2 is explaining 20%, and these are all the 170 something observations. What was it? 178 observations. and these are the loading vectors. And yeah, and this is the direction of the loading vectors. That's pretty much it. I think, yeah, last semester I was doing it differently. This semester, with the help of ChatGPT, I say, hey, I want to create the biplot using Sklearn package. It gave me this nice code, and then I liked it, so we can use it. Again, you can twist it in whatever way you want, but this part is easy peasy. So don't overthink about it. Just understand the theory of machine learning more deeply. Okay, so now let's look into an application of PCA, right? Okay, so we are going to basically use PCA as a pre-processing step for using it in a supervised machine learning model, right? So I'm going to use logistic regression for this example. And remember, there was this data set was labeled, and we have already had customer segments. So we can see, for example, if I use logistic regression with 13 features, what is the performance? If I use logistic regression with 2 features coming from principal components, what is the performance, right? So yeah, that's what we're going to do. So let's go ahead and this is a supervised part, right? Let's from scikit-learn linear models import logistic regression, and your target variable is customer segments. Your feature space is everything else. Just pretty much standard train test split sets. 20 test, 80% train, and then we're gonna scale the features. Scale the X train and X test. So let's go ahead and run this. And now this is our logistic. Let's create our logistic regression object. And because we have 3 class classification, we have to say multi-class is equal to auto. I think by default is auto, but I just wanted to show you that we can do logistic regression for a multi-class classification as well. By default, it's used for 2-class classification, but we can also use it for 3-class, 4-class, and etc. So here in this example, we have 3 customer segments, so it's going to be 3-class classification. And at the end of the day, we are going to do some cool visualization, right? If I work with 13 features, there's no way I can visualize the decision boundary, right? But if I use PCA and bring the dimension to 2, I can visualize the decision boundary in 2 dimensions, right? So remember, in the supervised machine learning part of the course, we did visualize all the decision boundaries, if you remember, with scikit-learn. The way that we were doing, we picked 2 of the features that we thought that are more important, and then we worked with those 2. But here, we are not selecting any of those features. We are extracting 2 principal components out of all the available features. So this sounds more reasonable, and this is exactly what PyCaret package is doing when it's visualizing the decision boundaries for a classification task, right? Okay, so yeah, let's go ahead and make some predictions. Oops, did I not run this one? Let's see. Okay, there you go. Now we have the predictions, we have the actuals. Let's look at some performance metrics. Again, if you feel that this is a little fast, we have done this many times before. So just pause the video, just think about it. You should be able to figure it out. All right, so the confusion matrix, this is the 3-class classification. The numbers on the diagonal are good numbers. So true class 1, true class 2, true class 3, or here in this case, true segment 1. And then off diagonal, these are the bad numbers. And this is a pretty good confusion matrix in a test set, right? There's only 2 misclass classifications. That's it. So the accuracy is 94%. F1 score is 94%. This is excellent. So the model is doing an excellent job. So our simple logistic regression using all the features, all the 13 features, is doing an excellent job. Accuracy F1 score 94%. All right, now let's go ahead and apply principal component analysis to bring the dimension of the data into 2 for visualization purposes. However, we're going to run the same logistic regression model with the new principal components and see what's the performance, right? So let's create an object PCA, 2 components. And now here's an important thing. We need to create the scores, right? Remember, we have to go from 13 features to 2 dimensions, to 2 principal component dimensions, right? So I'm going to go ahead and do fit transform X train. Remember, our X train has 13 features. If I apply this thing, we're going to have 2 components. So this is X train in 2 components. And we're going to do transform to X test as well. So for train, this is typical machine learning. For training things, we're going to use only train set, and then once the object has been trained, we're going to apply to the test set. So that's why in the test set, we're going to only see transform in order to make sure that we're not any kind of sort of cheating. Okay, actually, let me show you the dimensions and hopefully it helps. So train scores, if I look at the shape, so this is going to be number of observation and then 2 dimension. If I show you the X train thing, so the X train shape, this is going to be 142 observations, 13 features. So basically we are going from 13 dimension to 2 dimension. That's it. And now I need to just simply apply logistic regression to this new scores, these new features. Okay. All right. So remember, we have only 2 components, and those 2 components are explaining cumulatively 56% of the variation in the data. Okay, let's go ahead and train our model. Logistic.fit, again, this is the same logistic regression object, right, with 3 classes. Now, the only difference is that we are applying it to a new space, which is principal component space. That's it. Okay. And remember, the y's, the target variables, are just target variables. There are 1, 2, 3 segments. If we do that, we can go ahead and save the predictions. Now with the predictions and actual y's, we can look at the confusion matrix. In this case, surprisingly, the performance is pretty much the same as the case that we used 13 features. So just bear with me what's going on here. Up there, we used 13 features, and we saw that there you go. We used 13 features, and we saw that the performance of the model was 94% accuracy. Now, we reduced the dimension from 13 to only 2, and we still see that the model is doing a pretty good job. This was quite an accident here, okay? If I actually go ahead and change it to 3, probably the performance is going to get worse, because for logistic regression, and we only have 13 features. Yeah, there you go. So it goes from 94% to 91%, right? So the F1 also decreased. So in logistic regression with only the basically 13 features, it's a simple model. The more features you have, the better. So I don't expect principal component analysis to do any better than simple logistic regression using all the features, right? But here I'm happy because even with 2 principal components, it's doing a decent job, so we can use it for visualization as well, right? So this is basically what I talked about it. You can go ahead and create it. And by the way, if I use all the features, if I use all the 13 components, the answer is going to be exactly the same, okay? Because eventually you are explaining 100% of the variation in the data. All right, so some advanced visualization. This is the part that we're going to do some cool decision boundary visualization, right? Remember, if I wanted to use 13 features, we could not do this unless we manually select 2 of the most important features, but that's not a good idea. The better idea is that work with a combination of all those features, the extraction of all those features. PC1, PC2, and just go ahead and visualize the decision boundary. That's it. Okay. All right, and this is a confusion matrix in the test set. So we are going to find 2 misclassification, this one and this one. Okay, now finally, let's go ahead and look into the Kernel PCA. So in order to understand what the Kernel PCA do, you need to make sure that you have watched the theory lecture, because there we discuss the advantages and disadvantages of a simple linear PCA. And one of the disadvantages of linear PCA was that it is limited to linear transformation and of the features, right? So this means that it may not capture the intrinsic structure of nonlinear data, right? So we had to do is basically use some RBF kernel like some kernels like RBF, sigmoids, and polynomials, and you name it, right? Let's see how it's done in Python. So we're going to go ahead and import the relevant libraries, set the random states. This is a data set that we're going to work with. This is pretty straightforward. We have seen this data set before. And again, I'm using yet another supervised data set to show you one of the applications of Kernel PCA in machine learning, right? Actually, this is the very last slide, right? So this is what we talked about it in the theory lecture as well. I'm going to replicate these things. Let me actually give you a quick recap. So let me see if I can zoom in a little bit. The idea was that what if the data set was non-linearly separable, right? Something like that. And you wanted to use a linear classifier. So if I use a logistic regression, a linear classifier, probably it's not going to do a good job. So what are my options? I can use a non-linear classifier like decision tree base or Cannon. Cannon is going to shine here. Decision tree base is going to basically easily do the job. But we just say, for the sake of argument, imagine you want to use logistic regression. So what is your option? You can say, hey, yeah, let's go ahead and transform the data using Kernel PCA, capturing those nonlinearities. And in this new feature space, which is by PC1, PC2, which has already captured the nonlinearity, let's apply our simple linear logistic regression function. That's it, right? So that's why we're working with this data set. We're going to keep things very simple, so I'm going to go ahead and only pick age and estimated salary, only 2 features, and that's it. So we're going to rearrange it, and this is our target variable, purchased or not, right? Okay, so let's go ahead and first train our logistic regression with 2 features, right? So from Sklearn, import logistic regression. We need to scale the features. Again, we're replicating this thing. Everything is scaled here if you pay attention. Okay, so we're scaling the features. I'm going to go ahead. My target variable is purchased, and the x's are basically everything but purchase. So basically age and estimated salary. Okay, so let's do a simple train test split and then train the model. Then that's it. So this is in our original space. In our original space, we are just creating this decision boundary. Okay, that's what we did. So if I do y-hat predictions, so these are going to be, let me actually run it one more time. So these are going to be the predictions of the simple logistic regression model applied to our original space, x1, x2, age, estimated salary. Okay, now we're done with the first one, right? Now we can go ahead and create this one. For that one, we need to apply Kernel PCA. Okay. So let me remind you what is the shape of the data set. 400 observations, 2 features and 1 target variable. Our train set obviously had 2 features and then 320 observations. So I'm going to go ahead and import the Kernel PCA from Sklearn decomposition, and I'm going to create this object, call it KPCA. Kernel PCA, number of components 2, again because we want to do this visualization. And the kernel function that you're going to use is RBF. You can do RBF, you can do sigmoid, you can do polynomial, you can do linear. If I do kernel is equal to linear, this is going to be pretty much the PCA, right? So it's a linear kernel PCA is the same as using the PCA function. Okay, so just like the one that we did in the previous notebook, we are going to go ahead and create our transformed data set, right? So how do we do that? We say from this kernel PCA that you trained, let's go ahead and transform the X train. Let's go ahead and transform the X test. So we're going to save it as train PCA scores and train test PCA scores. Okay. So you can look, if you check the dimension, it's pretty much the same as this one, because remember, these are same dimensions, 2 dimension on the left, 2 dimension on the right, 320 observations. Okay. And actually, this is a test set, so what to get the idea. Yeah, now this is Kernel PCA. And if you remember from the previous notebook, we said that there's only one way to basically create the PVEs, right? Proportion variance explained. And that's by looking at the variation of the scores themselves, right? So how do we get the scores? So remember, this is Sklearn. So in order to get the scores, we have to do Kernel PCA dot fit transform, and then this is going to be your scores. Okay. So, and then we calculate the variance along the principal components, PC1, PC2. Okay. So let's go ahead and run that. These are your basically the variance, right, along those principal components. And if I look at the contribution of each variance to the total variance by doing this thing, it's going to give me PVE, right? So component 1, 54%, component 2, 45%. And obviously, if you do the cumulative version, it's going to add up to 1. Okay. So one thing I want you to pay attention is that if you go back to the simple PCA in Sklearn, And if you, for example, try to, let me actually show you something. Imagine you have 13 features, right? If you try a number of components, anything greater than 13, it's going to complain. However, in Kernel PCA, it does not complain. So let me tell you why. So imagine, remember, we have only 2 features. And if I do 100, you expect that, is it able to go? Actually, let's keep it simple, 10. We don't have 10 features. So how come you end up having 10 principal components? Because if I run it, it's not going to complain. So what's going on here? So remember, in the Kernel PCA, there were 2 steps. Where is it? Okay, we have to go ahead and create the kernel transformation, and basically that's when we talked about the kernel matrix, and the dimension of this thing was basically number of observations multiplied number of observations. So if I have 400 observations, I can go all the way to 400 principal components, because that's the dimension of your kernel matrix, and that's what's happening here. So that's why you can go above the number of features. Okay, so that was just something for those of you who are interested, why you're not getting any error when you add more components here. Okay, so yeah, let's go ahead and fit the logistic regression to the transformed data set, right? Okay, and make some predictions. So I'm going to call these predictions Y PC prediction test. For the previous one, we call it Y prediction test. For this one, we call Y PC prediction test, right? Okay, so let's look into the confusion matrix for both of these models. Again, I have 2 models, this one, the one on the left, the one on the right, and we can look at the performance, right? So we are going to look at the performance of the, this is the kernel PCA first, right? So it's doing, let me actually add, yeah. So the kernel PCA is doing a decent job, right? Precision 79%, recall 69%, and F1 score 73 with the accuracy of 80%, okay? So we can, again, we can visualize these things. Well, actually, before doing that, let me show you the report for simple logistic regression as well. I can do Y, well, this should be Y test. So let's not touch this one. This should be, yeah, that's it. Okay, so this is a performance of the simple logistic regression. This is a performance of logistic regression applied to transform data. Okay, and as you can see, this I don't know, the transform version has a higher recall, but precision is lower. F1 is the same, and accuracy is pretty much the same. Okay, so we didn't get much improvement here in this example. There's still lots of misclassifications here, and this is a sign that maybe that was not a good idea to necessarily use that kernel PCA trick. You can play around with different kernels. For example, you can do polynomial and etc., etc. But I think for a simple task like this, when you have the luxury to visualize the data, I know that for a fact we can use KNN, we can use random forest, we can use decision tree base, and it's going to do an awesome job in this simple task. Okay. So, and then we can visualize it. So this is a visualization that we talked about in the theory lecture. So first, the one on the left, original space and logistic regression. So our logistic is going to be this, trained on the original space. We can visualize it. And the second one is this logistic regression trained on the kernel PCA thing, features. And then let's do that, and let's do the visualization. This is what we get, right? So that's basically what we talked about it here. All right, so yeah, and I already calculated these, reported this confusion matrix for you, or classification reports. All right, so that was pretty much it. I know it's been a long one, and we covered 3 notebooks, but at the high level, I think when it comes to principal component analysis or any other machine learning models in general, you should learn the theory deep down. Don't worry about the Python too much. You will figure it out. But the theory is something that you need to sit and think about it deeply. All right, I hope you enjoyed it. Until the next one, take care.